Imagine a bearing, larger than a passenger car, that operates without service for 100,000 hours and turns a 5-megawatt wind turbine. Its balls are polished to a precision of 4 millionths of an inch. The melting point of the steel used is almost 3,000 degrees Fahrenheit. Manufacturing it requires factories the size of cities, cranes that lift railroad cars, and presses that squeeze metal like modeling clay. But that's just the beginning. What you are about to see isn't just production. This is industrial magic that holds the whole world together. Where does a giant industrial bearing begin? Not with a blueprint, not even with a machine tool. It all starts with metal. But not just any metal. Special grades of steel are used for bearings, and their chemical formulas are sometimes guarded as trade secrets. Most often, it's chromium or alloy steel with enhanced strength, resistant to extreme pressure, vibrations, friction, water, and even time. The ore from which the steel is smelted arrives from different corners of the globe. It's often extracted through open pit mining, from enormous quarries where dump trucks have wheels as tall as a 2-story house. Then, the ore is delivered to metallurgical plants. These are cities in miniature that operate without sleep or weekends. In blast furnaces, the ore is melted at temperatures close to 3,000 degrees Fahrenheit. Alloying elements like chromium, manganese, and molybdenum are added, and the molten steel is poured into molds, creating large steel ingots. But this isn't a bearing yet. It's just raw material. Next, the ingots are cut into pieces, rolled, heat-treated, and transformed into so-called rings, blanks from which the bearing will eventually be machined. They are transported by special trailers or by rail to machine building plants. A single blank can weigh a ton, and moving it requires a crane. Precision and quality start right here. Any crack, dent, or internal inconsistency, and the entire batch can be rejected. That's why materials undergo rigorous inspection at the factory: visual, ultrasonic, and magnetic particle inspection. The production of a giant bearing forgives no mistakes. Everything must be nearly perfect. Such giant industrial bearings, larger than a passenger car and weighing over 3 tons, are used in heavy-duty equipment. For example, in wind turbines. In the mining industry, huge bearings rotate in crushers, mills, and mining conveyors. In metallurgy, they are used in rolling mills and blast furnaces. Offshore platforms and ships, cement plants, hydroelectric power stations, oil extraction, all require extra-large, super-strong bearings. After all, they withstand extreme loads, rotate with immense force, and operate in aggressive environments where smaller parts simply wouldn't survive. After the metallurgical plants deliver the steel ingots, each weighing tens of tons, to the bearing manufacturing facility, the magic begins. These ingots don't have any shape yet, but they already conceal future strength. Giant cranes lift them. One such hoist can support the weight of a railroad car, and with precision down to the inch, lowers the red-hot blank to where they will start sculpting the bearing from it. The scene looks like something from a science fiction movie. Massive hydraulic presses with thousands of tons of force squeeze the metal like modeling clay. It's rolled, pressed, heated again, and it begins to transform into a huge metal ring, rotating on a conveyor. Every movement is accompanied by roars, clangs, and hissing steam. Heating furnaces heat the steel up to 2,000 degrees Fahrenheit. That's almost twice what's needed to melt lead. Workers in protective gear look like characters from a post-apocalyptic movie, and for good reason. One spark could cause serious injury. But thanks to automation and strict safety standards, everything proceeds exactly according to plan. As soon as the ring takes shape, its machining begins. Like a giant potter's wheel, it spins on lathes that, with a screech, shave off layers of metal mere thousandths of an inch thick, grinding the surface to a perfect smoothness. There's no room for error here. Even a tiny inaccuracy can be fatal at the speeds these bearings rotate. Behind every giant bearing stands a team that knows every part of the process inside out. These are engineers, technicians, and master craftsmen who study blueprints, check temperature regimes, lubricate parts on time, and monitor precision down to the micron. Some have worked here for decades. Their hands are covered in grease, their eyes are tired but intense. And despite the noise, the risks, and the difficulty of the work, many wouldn't trade this rhythm for anything. The first massive bearings appeared in the 20th century, when industry began to grow taller and wider. Hydroelectric turbines, rotors in oil refineries, tower cranes, all needed reliable rotators for colossal loads. After grinding comes the most critical part: quality control. The giant bearing undergoes a thorough inspection, like an athlete before the Olympics. Its surface is examined for microcracks using ultrasonic sensors and magnetic particle inspection. The massive ring lies in a special bath, and waves and magnetic particles are passed over it. They'll glow in places where there's even the slightest damage. Then comes balancing. The huge metal structure is mounted on a special stand resembling giant scales. The bearing starts to rotate, slowly at first, then faster. Computers detect any imbalance, and technicians add or remove metal in the necessary places. Everything is done so that in the future, this bearing can operate at tremendous speeds without the slightest wobble. Inside an industrial bearing are steel balls or rollers. Each ball starts as a small metal cylinder, a wire rod, about 1/2 inch to 2 inches in diameter. It's cut into blanks, and then cold heading is used to form the future ball, still with noticeable seams and roughness. At this stage, the blank weighs from 1/10 of a pound to 1.5 pounds, depending on the size. These blanks are called flashes. Next is the tumbling process, where the blanks are passed between two discs spinning at incredible speeds, up to 1,800 revolutions per minute. This removes the seams and achieves a more perfect shape. Then comes heat treatment at 1,500 degrees Fahrenheit to give the steel strength, and only after that, the finest grinding. The balls are ground on high-precision machines, with a tolerance no greater than 4 millionths of an inch. Polishing takes 48 hours, and the final result is a ball that can rotate millions of times without wear. A similar process applies to rollers. They are machined from high-strength steel, can be up to 8 inches long, and withstand loads over 10,000 pounds per square inch. They are also ground, heat-treated, and each undergoes individual geometry checks. After manufacturing the rolling elements, it's time for assembly. Between the outer and inner ring of the bearing, a separator is installed, a special cage that evenly spaces the balls or rollers. Separators can be steel, brass, or polymer, depending on the application. For instance, polyamide cages are often used in wind turbines due to their moisture resistance. A typical bearing for a 5 megawatt turbine might contain around 70 balls with a diameter of 2.5 inches, or 30 rollers 6 inches long. In the final stage, the assembly is lubricated, using grease with an operating temperature range from -40 degrees Fahrenheit to +400 degrees Fahrenheit. Seals or protective shields are added, and the bearing is ready for work, designed to last 100,000 hours without service. Global leaders in bearing production manufacture enormous volumes. For example, the Swedish company SKF produces 600 million bearings annually. The Japanese company NSK produces approximately 1,250,000 bearings per year. The main challenges facing the bearing industry relate to the high demands on materials and technologies, the need for strict quality control, and the constant implementation of innovations to maintain competitiveness. Fluctuations in global raw material prices, competition in the global market, as well as the need to improve energy efficiency and reduce production costs create additional difficulties for companies in the sector. Imagine taking the air you are breathing right now and turning it into a substance that can freeze ice cream in 3 seconds and make a banana tough enough to hammer nails. This is not magic. It is liquid nitrogen. Every second, it is used in medicine, science, the food industry, and in some top-secret experiments. Temperature, -321 degrees Fahrenheit. One sip and you lose part of your stomach. One breath and you unlock tomorrow's technology. How does the coldest substance on Earth get made from regular air? How is it transported, stored, and used? And why can it save or destroy? Watch closely and prepare to be amazed. It all begins with air. Yes, the very same atmospheric air that surrounds us. This happens inside industrial air separation units. These systems come in all sizes, from massive factory installations to mobile units for medical use. Air is sucked in using compressors. Then it passes through filters. First, coarse filters that remove dust, insects, and pollen. Next, fine filters get rid of moisture, carbon dioxide, and other impurities. Once cleaned, the air is compressed using powerful machines, increasing both pressure and temperature. Then, it is gradually cooled in heat exchangers. When the high-pressure cooled air moves through a narrow nozzle into a low-pressure chamber, it expands rapidly. That sudden expansion causes a major drop in temperature. This is the key moment. The gas becomes cold enough to start condensing into a liquid. This process repeats several times. Each cycle drops the temperature further. Eventually, nitrogen reaches its liquefaction point. This technique does not work with every gas, but it is perfect for nitrogen. Thanks to this, we can create liquid nitrogen from ordinary air. Once the air is chilled and liquefied, it goes through fractional distillation. This process separates the liquid mixture into components based on their boiling points. Inside a special distillation column, the liquid air is gently reheated. Nitrogen has the lowest boiling point, around -320 degrees, so it evaporates first and rises to the top. Oxygen boils at -297 degrees, so it evaporates later and does not climb as high. Argon, with a boiling point around -302, settles somewhere in between. The column forms a thermal gradient, colder at the top, warmer at the bottom. The gases evaporate and condense over and over, becoming purer with each cycle. It all works without additives, automatically, and with minimal losses, thanks to precisely managed pressure and temperature. Since nitrogen makes up roughly 78% of air, extracting it takes powerful equipment, a complex network of pipelines, and exact temperature control. Once separated, liquid nitrogen is stored in special vessels, cryostats, or Dewar flasks, which look like futuristic thermoses. These vessels keep temperatures low and prevent evaporation. They are not just metal barrels. They have double walls with a vacuum in between to block heat. Some also include reflective coatings to minimize radiant heat loss. These containers can preserve liquid nitrogen for several days to several weeks, depending on volume, insulation, and how often they are opened. Often, nitrogen is used right on site. For example, medical facilities use liquid nitrogen for cryopreservation of cells, embryos, vaccines, and tissues. In the food industry, it is used for flash freezing. Contact with liquid nitrogen instantly freezes food, locking in texture, taste, and shape. But when it needs to be transported, preventing evaporation is critical. That is because nitrogen quickly turns back into a gas. Portable dewars, cryotanks, and cryotank trucks are used. Small dewars are handy for labs and clinics. Cryotanks are massive, like giant gas tankers, and are hauled by trucks with special mountings and ventilation. Cryotank trucks are purpose-built vehicles with insulation and pressure regulation to avoid explosions from expanding gas. Sometimes, liquid nitrogen is produced directly on site, at large research centers or hospitals, to avoid reliance on deliveries. How did humanity tame one of the coldest, most inert substances on Earth? It all began with nitrogen. Discovered in the year 1772 by Scottish chemist Daniel Rutherford, who was studying air and found a gas that could not sustain fire or life. That was nitrogen, colorless, odorless, inert. But liquefying it required cold and pressure, and humanity needed more than 100 years to figure that out. The first liquid nitrogen was produced in 1883 by Polish scientists Zygmunt Wroblewski and Karol Olszewski. They built a system that cooled air so much that nitrogen, its main component, turned into a liquid. That was a breakthrough. In the 20th century, cooling tech advanced fast. Scientists improved gas liquefaction methods and eventually developed the Joule-Thomson cycle, which relies on pressure drops to efficiently liquefy gases. In the 1930s and 50s, liquid nitrogen made its way into industry and medicine, starting in labs, then into surgeries, biobanking, and physics experiments needing ultra-low temperatures. Today, liquid nitrogen production is a global-scale operation. It is made in massive air separation plants around the world. What was once just background gas, making up almost 80% of air, has become a superstar of industrial science. Some chefs even make ice cream live, pouring cream into a bowl, adding liquid nitrogen, mixing, and voila, instant dessert. The cold is so intense, it freezes the treat in seconds. Dip a banana in liquid nitrogen for a few seconds, and you can hammer nails with it. Seriously. Want to try? Inhaling cold nitrogen vapor can temporarily change your voice, like helium, but deeper. But do not try this. It is dangerous without protection and special equipment. Some people have dipped old socks into dewars of liquid nitrogen. Result? The fabric becomes brittle like glass and crumbles in your hands. A perfect way to destroy evidence. If you are a sock. Pour liquid nitrogen on a warm floor, and it turns into a dramatic cloud. It vaporizes instantly, making you feel like you are stepping through a Hollywood portal. What should you never do with liquid nitrogen? Even if it looks cool? Never stick your hand into it. Online videos show people dipping fingers and pulling them out unharmed. That is the Leidenfrost effect. A brief protective vapor layer forms around the skin, but if you hesitate for a second too long, hello frostbite, do not try it. Seriously. Never drink it. Yes, that happened too. In several restaurants, smoky desserts were served with a drop of liquid nitrogen. One careless guest sipped before it had fully evaporated and lost part of their stomach, literally. Afterward, several countries banned such stunts. Do not pour it on your bathroom floor. The vapor looks cool, sure, but tiles can crack from thermal shock. Plus, the risk of suffocation in a small space is real. Nitrogen displaces oxygen. Do not pour it in the toilet. Not because it will definitely break, but it might. And because pipes can burst. Some TikTokers have proudly frozen their plumbing. Utility crews must love them. If you are not an engineer or a molecular gastronomy chef, do not try freezing food or fruit from the inside. Liquid nitrogen can rupture the skin and explode in your hands, especially with high moisture items. So yes, liquid nitrogen is amazing, but it is also incredibly dangerous. Respect the frost. Every year, over 2 billion cacti are grown around the world, and we are not just talking about your grandma's windowsill plant. They are crushed into cosmetics, tossed into salads, turned into textiles, and even transformed into cactus leather. The largest plantations stretch across thousands of acres in Mexico, Italy, and the United States. These plants grow without a single drop of irrigation, absorb carbon dioxide better than trees, and thrive in places where even weeds seem exhausted. Cacti are charging into the future, and not just in flower pots. In this video, we will show you how they are grown, why the world needs so many cacti, and how they might just help save the planet. In the United States, cacti have long outgrown the souvenir market. They are cultivated for cosmetics, pharmaceuticals, bioleather, livestock feed, and even as an edible superfood. While most people associate cacti with Mexico, it is actually the United States that has become one of the leaders in industrial cactus farming. The United States was not always at the top in this field. Mexico traditionally held that title, where cacti are a national plant, a food source, and a cultural symbol. But starting in the 2000s, when the global boom for superfoods, vegan products, and eco-friendly materials began, American farmers and startups saw a golden opportunity in cactus farming. They figured, quite reasonably, that the climates of Texas, Arizona, and California are ideal for growing prickly pear, nopal, and other species. Plus, the United States has a huge market of consumers seeking healthy, vegan, locally produced goods. So, the demand was already there. Many agricultural startups received grants, investments, or government support to launch sustainable cactus farms. Fast logistics, existing processing infrastructure, and support for small agribusinesses all played a major role. By the 2010s, especially after 2015, farms started popping up not just for food, but for cosmetics, medicine, and leather. And since 2020, when the world embraced alternative materials and zero waste, the United States has stormed into the top producers of cactus-based bioleather. Now, American plantations supply products both domestically and for export to Europe and Asia. The largest plantations are found in Arizona, Texas, California, and New Mexico, regions with dry climates, lots of sun, and very little rain. In Maricopa County, for example, cacti are cultivated across dozens of acres of open land. The main variety here is prickly pear, prized for its fast growth, edible fruits, and industrial applications. It all starts by selecting the hardiest, most productive cacti, those that have shown strong resistance and consistent yields. For instance, a single prickly pear plant can produce 20 to 30 fruits in one season. Farmers cut a segment from the parent plant, usually one pad or shoot, and dry it for 3 to 10 days so the cut seals and does not rot in the soil. These cuttings are then planted in a sandy clay substrate, sometimes directly in open fields, sometimes in containers for rooting. The rows are spaced 3 to 5 feet apart to allow equipment access and minimize light competition. Cacti take 3 to 4 weeks to root, and the first fruits or shoots appear after 6 to 12 months, depending on the variety and climate. During that time, farmers monitor humidity and temperature. Once the first plants are well established, the farm expands by taking new cuttings from these fresh plants. This creates a stable, nearly self-sustaining system. So, it all begins with one spiky stalk, and within a year, it can produce dozens of new ones. To keep a cactus field looking like a postcard-worthy Mexican paradise, it needs real maintenance. Sure, cacti are desert survivors, but once you grow them by the ton, they become a little more delicate than the ones on your windowsill. On a commercial scale, drip irrigation is used, a system of tubes that slowly but steadily waters each plant. The average is 4 to 8 gallons per plant per week, depending on the climate. Next comes pest protection. The biggest threat is not rain, but cochineal. This fuzzy white bug looks like a cute puffball, but drains the sap out of plants faster than you chug a smoothie on a hot day. Then there are spider mites, nematodes, and other microscopic monsters. What do farmers do? They use biocontrol. They release predatory insects to hunt down the pests. It is like Game of Thrones, in bug form. Sometimes they also use natural insecticides, like garlic-based sprays or neem oil. Cacti prefer nutrient-poor soils, but a little boost never hurts. Once a season, farmers add compost or a special blend of nitrogen, potassium, and phosphorus. It is all done by the book, between 11 and 22 pounds of fertilizer per acre. Otherwise, you will end up with a jungle, not a farm. Harvesting on large cactus plantations is not some old guy with a machete. It is a full-blown operation. Harvest usually happens in the morning, before the sun turns the fields into a frying pan. Workers wear protective gear, because those spines are no joke. They trim ripe fruits or pads with special knives, or even mechanized tools. One person can harvest between 1,000 and 1,500 pounds of raw material a day. And if the farm is automated, that number can double. The most popular varieties, nopales and tuna, go on to be sorted. Each plant gets inspected: size, weight, color, and damage. Some fruits are automatically weighed, scanned, and sent down a conveyor. Premium ones head to supermarkets. The rest go to processing or canning. Workers manually inspect up to 1,000 units per hour, so the concentration level is like the final scene of a TV drama. The biggest farms use computer vision systems that sort out defects and count yields. Sorted cacti are packed into boxes or plastic crates, labeled and prepped for shipping. Shipping cacti is all about delicacy and timing. Packed in ventilated containers, they are loaded into refrigerated trucks. The temperature stays between 40 and 50 degrees Fahrenheit to prevent the cacti from turning into mush. On average, one truck carries about 40,000 pounds of product. If it is for export, cacti may travel thousands of miles to Europe, Canada, or Japan. To keep everything fresh, logistics must be timed down to the minute, and a little bit of luck helps. No one wants to open a box of shredded, spiky bits instead of bright green segments. Young prickly pear pads are no longer exotic. In major supermarkets in California, Texas, and Arizona, nopales sit right next to broccoli and romaine lettuce. And yes, they go on sale on Fridays. They are often sold pre-cleaned and sliced into strips, cubes, or thin rounds, or pickled in jars with peppers, garlic, and onions, basically like Mexican pickles. Nopal juice or powder is added to smoothies and supplements. It is good for digestion, helps manage blood sugar, and is considered a superfood. Fried with eggs, cactus is a classic breakfast dish. Think of it like Mexican scrambled eggs with a tangy green twist. It also goes in tacos and burritos, adding texture and a slightly slimy but pleasant acidity. Prickly pear tastes great in salads with tomatoes, feta cheese, peppers, and cilantro. It is also baked with cheese or meat as a side dish, or turned into cactus lasagna. The taste? Well, it is an acquired one. A bit like green bell pepper, a bit like beans, with a slight tang and a slippery texture, if you do not roast it well. But once you try it, you often come back. Do you like the taste of nopal? Share your favorite recipes. If you think cacti are just about spines and sand, you're missing the big picture. They store water in their stems for years. Like real soil-based banks, they hold reserves for hard times. In deserts, they become water distributors for entire ecosystems. Nopal, like many other cacti, is also used in folk medicine for treating everything from diabetes to digestive issues. Its gel helps heal wounds and prevents scarring. In some countries, cactus-based cosmetics are common. Nopal gel is often found in moisturizing creams and serums. Its texture allows it to penetrate the skin quickly without leaving a greasy residue. It is known that nopal extract has a calming effect, helping reduce inflammation from sunburns or skin irritation. The oil extracted from cactus seeds, especially prickly pear seeds, has become a star ingredient in cosmetics. Rich in fatty acids and vitamin E, it is a powerful antioxidant. Prickly pear seed oil helps reduce wrinkles and improve skin elasticity. It also soothes and nourishes the skin, preventing dryness. That is why it is often added to eye creams, where it helps reduce dark circles and puffiness. Cactus extracts are also used in hair products. The oil and nutrients help strengthen hair, add shine, and improve scalp health. They may reduce hair loss and stimulate growth while moisturizing dry scalps. Some cactus-based products even offer UV protection. Extracts can form a natural barrier against the sun's harmful rays, helping prevent sunburn and irritation. Brands like Kiehl's, Fresh, and Herbivore Botanicals already use cactus extracts in their products. Facial creams, serums, shampoos, and hair masks featuring cactus are especially popular. Nopales can live for decades. Some cactus species even live for centuries. For example, the saguaro, the giant cactus, can live up to 200 years and grow to 40 feet tall. That is about 1 inch of growth every year. And it is not just the stems that are edible, the flowers are too. Prickly pear flowers, which often bloom red or orange, can be tossed into salads, brewed as tea, or used as edible decorations on dishes. As of the year 2025, approximately 135 million monitors are shipped to markets worldwide every year. This includes both new models and replacements for old ones, as part of a typical 4 to 5 year tech upgrade cycle. While it is difficult to pinpoint the exact number of monitors in global use, due to varying lifespans and growing demand, it is estimated to be in the billions. That is because as much as 66% of the global population uses computers. But what happens when it is time to recycle a monitor? Cathode ray tube monitors, those old bulky screens, were common before flat screens took over. They contain glass with high lead content, phosphors, and electronic components. Lead in the glass can make up as much as 20% of a monitor's weight. Sounds dangerous, right? Light-emitting diode, or LED monitors, are the modern flat screens that use LEDs for backlighting. They are lighter and more energy efficient, but still contain plastic, metal, and rare earth elements. Guess what? Mishandling these monitors can cause serious environmental problems. Lead from CRTs can leak into soil and water, and plastic from LEDs can take centuries to decompose. That is why recycling is not just a trend, it is a must. In the United States, over 4,400 million pounds of e-waste is generated every year, but only 25% is recycled locally. Every single day, Americans throw away more than 500,000 computers and mobile devices. This creates a massive environmental challenge. Electronic recycling centers, like Repowered in Minnesota, play a key role in addressing this issue. Each year, they process about 3 million pounds of electronics, which makes up 5% of all electronic waste collected in the state. Impressive, right? These centers accept any device with a cord, except for large appliances, and ensure proper disposal or reuse. Some states, like California, go even further. There, it is illegal to dispose of e-waste in regular landfills. California has over 600 drop-off locations, and recycling is funded through a fee on the sale of new monitors and televisions. By the way, California spans around 163,696 square miles. It is the third largest state. Trucks are loaded with old monitors and driven to recycling centers. This method is typically used for short and medium distances. For long hauls, container shipping is used. It is more cost-effective and safer for large volumes of electronics. At the plant, monitors are unloaded in the intake area, where trained staff inspect them for hazardous materials and evaluate their condition. The monitors are disassembled into key components, such as cathode ray tubes, display panels, power supplies, and other electronics. This process can be done manually or with specialized equipment. The separated parts are sorted by material type. Casings, power supplies, and other metal components are separated for further recycling. Recycling metal parts from monitors looks like a full-on industrial operation. Massive machines work in sync to turn scrap metal into something new. Shredders roar. Furnaces blaze. The air is thick with the scent of molten metal and the noise of industry. Metal components are cleaned of contaminants like paint, plastic, and other non-metallic materials. This is done with machines that strip away surface layers and boost metal quality. Rotating brush systems or dedicated surface cleaning machines are used. This step can also involve shredding, crushing, or other mechanical methods. Metals might also be treated with chemical solutions to remove corrosion and other residues, using acids or alkaline solutions to dissolve unwanted layers. Then, the metal is shredded into smaller pieces using large presses or industrial shredders. This makes it easier to process and transport. Next, metals are sorted by type. Ferrous metals are separated from non-ferrous ones. Each metal type requires a different recycling process. The metal pieces are then melted down in giant furnaces at high temperatures. Steel melts at about 2,552 degrees Fahrenheit, while aluminum melts at around 1,112 degrees Fahrenheit. As the metal melts, impurities are removed, and the material is poured into molds to form new ingots. These ingots are used to manufacture new metal products like construction materials, car parts, or home appliances. Using recycled metals cuts production costs and preserves natural resources. At smelting plants, huge conveyor lines move metal pieces through different recycling stages. Workers in full protective gear oversee the process to ensure safety and quality. Thanks to this effort, old monitors are reborn as new, useful products, helping the environment and advancing sustainability. Plastic components from monitors and other electronics are collected and sorted by type, usually polycarbonate, acrylic, and polystyrene. They are shredded into small pieces using machines like industrial shredders or crushers. This makes the plastic easier to transport and process. The shredded plastic is then cleaned to remove contaminants and impurities. This step uses air jets, magnets, or other tools, depending on the plastic type. The clean, shredded plastic is melted and molded into pellets. These pellets become the raw material for making new plastic goods. In the United States, about 6,600,000 pounds of plastic are recycled annually. That is only around 8% of total plastic waste. But those recycled pellets go on to make more than 100 million new plastic items every year. Shredders and crushers roar as they grind plastic. Conveyor lines move the material through different stages of processing. Recycling plastic saves about 88% of the energy compared to producing new plastic from raw materials. A typical CRT monitor contains almost 3 pounds of lead in its glass. The leaded glass is separated from the monitor's other components. The cathode ray tube is disassembled into individual parts: the screen, the funnel, and the neck. The screen is made of activated glass, while the funnel holds the lead. The glass is cleaned of phosphor and other residues using chemical solutions or mechanical methods. After cleaning, the glass is homogenized. During this stage, you can see giant rotating drums scrubbing paint and resins from the surface. The glass is then sorted by size and sent off for further processing. Thanks to this method, old leaded glass gets a new life while supporting sustainable development. The glass is melted down in special furnaces at high temperatures. Lead is extracted and purified from impurities. This clean lead is used to manufacture new products like batteries, ammunition, or building materials. So yes, it is possible your old monitor might one day help protect the country. Now let us move on to recycling circuit boards. Printed circuit boards are shredded using machines like hammer mills or industrial shredders. This helps extract most of the metal content. The resulting material is usually smaller than 2 inches in size. This shredded material is passed through magnetic separators and air jets to separate metal from non-metal elements. Metals like copper, gold, and silver have unique physical properties that allow for efficient separation. Chemical extraction methods are used to recover the metals. For example, gold and silver are dissolved using acidic solutions. These solutions are then processed to obtain pure metals. Another method involves heating the circuit boards to high temperatures to burn away the non-metal materials and extract the metal content. However, this method can release toxic gases, so it is used with strict safety measures. During chemical recovery, you might see massive tanks filled with acidic solutions where metals are being separated. After extraction, the metals are purified and formed into ingots for manufacturing new goods. Through this process, old circuit boards are reborn as new, useful materials, supporting sustainability and protecting the planet. LED display panels can be recycled for use in making new screens or other electronic components. While the process is complex and not always cost-effective, it is seen as a promising path forward. Some LED monitors contain rare earth elements, which can be extracted and reused. Recycling LED monitors saves up to 70% of the energy compared to making new items from raw materials. Imagine a plant spread out over 11 million square feet, where thousands of specialists work every single day to assemble an aircraft made up of more than 4 million parts. Here, in Toulouse, France, giants of the sky are born, from the legendary A380 to the cutting-edge A350. Parts for these aircraft come in from all over the globe. Wings from Britain, the fuselage from Germany, and engines from the United States. This is not just a plant. It is the heart of European aviation and a true marvel of engineering. And now we are going to take a look inside. The Airbus plant in Toulouse covers an area of over 11 million square feet. Now, that is an impressive size for any manufacturing complex, and especially so in the aviation industry. This plant produces not only the A380, but also other aircraft models from the company, like the A350. To produce these technological wonders, Airbus uses more than 2,000 workstations equipped with the very latest technology. This plant is the heart of Airbus aircraft production and a complex logistics hub, where every stage of aircraft manufacturing is its own form of art. The Airbus plant in Toulouse was actually founded way back in 1946 under the name Aerospatiale. Initially, it was a French company specializing in aviation manufacturing, and it laid the groundwork for the future Airbus plant. All the early stages of the plant's operation involved creating aircraft for both military and commercial needs. The Toulouse plant was strategically chosen for its location, which provided convenient access to transportation and logistics routes within France and across Europe. Originally, the plant focused on developing smaller aircraft, but over time, it expanded its capacity and implemented new technologies to produce large passenger aircraft. In 1970, the company Airbus Industry was established, a consortium that brought together 4 major European aviation companies: Aerospatiale from France, Deutsche Airbus from Germany, Construcciones Aeronauticas from Spain, and Air Italia from Italy. From that point on, the history of the Toulouse plant became closely linked with the development of the aviation industry in Europe. This is where the production process for Airbus aircraft began, aircraft that would become significant competitors to giants like Boeing. Over the following decades, the Toulouse plant expanded multiple times as aircraft production really picked up speed. In the late 1980s and early 1990s, the plant became the main hub for producing aircraft like the Airbus A300, the first certified wide-body aircraft, and the A320, one of the most popular aircraft in the history of civil aviation. Over time, the Toulouse plant became the primary production center for models like the A330, the A340, and the A380, that huge double-decker aircraft that became a symbol of Airbus. In the 2000s, the Toulouse plant underwent major changes and modernization to handle the production of newer models, like the A350, which was introduced to the market in 2013. For this purpose, new assembly halls were built at the plant, including large facilities for assembly and testing, along with new automation systems to boost production efficiency and precision. Manufacturing the Airbus A380 is such a complex and detailed process that it requires innovative methods and technologies for its assembly. Just imagine, each aircraft produced at the plant consists of over 4 million individual parts. These parts are supplied from all around the world, from China to the United States. For example, the main fuselage components come from Germany, the wings from Great Britain, and the tail section from Spain. That is right, the Toulouse plant primarily handles the final assembly of the aircraft. This is standard practice for major aircraft manufacturers. Major engine manufacturers, like General Electric and Pratt & Whitney, supply the powerful jet engines for Airbus aircraft. Additionally, various aviation systems and components arrive from the United States. China is a key supplier of various metal parts, plastic components, and other materials for the aviation industry. Furthermore, Chinese companies provide certain aerodynamic parts. Other parts, including structural elements and fuselage details, are supplied by various European countries, such as Germany, Italy, Spain, and Great Britain. Well-known Canadian companies, like Bombardier, also supply components for different Airbus models, notably for the A220. After being manufactured, these parts are transported to the plant in Toulouse, where they are assembled into a single, complete unit. This often takes several weeks, and the large components are transported using specialized methods, like ships or air transport. The Airbus plant in Toulouse covers an area of 11 million square feet. It is one of the largest aviation manufacturing sites in the world. First, inside the plant's enormous assembly halls, the aircraft fuselage is put together. This is the main body of the aircraft, composed of several large segments that are delivered separately. Each fuselage segment is a major part of the structure, joined together with the others using cranes and specialized assembly machines. A crane lifts the parts, and they are carefully connected using special bolts and welding techniques. This is how the frame structure begins to take shape, although it is not yet in its final form. Once the main fuselage sections are assembled, the wings are brought into separate areas for installation. These wings are heavy, and their installation also involves the use of hydraulic cranes. When the wings are ready, they are attached to the main fuselage structure. Special attention is paid to this stage because the join between the fuselage and the wings is a critically important part that affects the aircraft's aerodynamics and safety. The installation of all the necessary systems, electrical, hydraulic, and avionics, also happens during this phase. Parts are integrated in special clean rooms to prevent any damage or contamination. This is a highly precise process, as all the elements, like cables, pipes, and computer systems, must be correctly positioned within a limited space. Robotic systems are often used at this stage for the precise placement of these elements. Once the aircraft structure is nearly complete and all internal systems are connected, it is time to install the engines. This is another critically important step, as the engines play a significant role in the aircraft's overall stability. Large hydraulic mechanisms and cranes are used to lift the heavy engines and precisely attach them to the aircraft structure. This also demands a high degree of precision and care. As soon as the aircraft is assembled and the engines are in place, it undergoes a series of tests and checks. On the ground, they conduct tests on the braking systems and check the aircraft's response to mechanical stresses. All these operations take place on enormous testing grounds, which allow for trials involving various loads and speeds. At the same time, the functionality of all the aircraft systems is verified. The testing area itself covers about 2 million square feet. After all the tests and adjustments are done, the aircraft moves on to the finishing stage, where it gets painted and the final details are added: window sealants, stripes, logos, and other design elements. Before the paint is applied, the aircraft is thoroughly cleaned to remove any contaminants, grease residues, or dust. Following this, the metal surface is treated to ensure better paint adhesion. An important step is the application of an anti-corrosion coating, which protects the aircraft body from oxidation and other harmful factors. This coating is applied using special sprays or spray guns to create a uniform protective layer. The aircraft is then painted in several layers. Most often, special polyurethane paints are used, which provide a durable, resistant coating. These are applied using rotary atomizers, which allow for even distribution of paint across the entire surface. The aircraft is placed inside a special painting hangar, sort of like a large enclosed area, where the necessary temperature and humidity levels are maintained to ensure proper paint adhesion to the surface and facilitate quick drying. After the base color is applied, a top coat is added, which provides extra protection against atmospheric elements and also gives the aircraft a glossy finish. This layer also adds resistance to ultraviolet rays, preventing the paint from fading in the sun. After painting, the aircraft are inspected for any defects. If any cracks or bubbles appear in the paint, they have to be corrected. In the final stage, airline logos or special liveries are applied to the aircraft. This might involve not just applying paint, but also installing special decals or applying a protective film to the surface. This process can take up to several weeks for a single aircraft, depending on the size and complexity of the livery. In total, painting a complete Airbus aircraft requires about 3,300 pounds of paint. The process of installing the cockpit is one of the most complex and precise operations. The aircraft cockpit, especially in models like the A350 or A380, contains hundreds of different sensors, control systems, displays, and other technical elements that must be precisely configured. Altogether, a cockpit can contain up to 5,000 different parts. Interestingly, the assembly of the cockpit takes place separately from the main aircraft body. This is done in special workshops where the cockpit is fully equipped before being transported for final integration into the aircraft. The entire cockpit installation process takes several days and demands the highest level of precision, because any malfunction in the control or navigation systems could lead to serious problems during the aircraft's operation. Another crucial aspect is the integration of avionics, which are the aircraft's electronic control systems. These systems allow pilots to monitor flight parameters, engine status, the situation in the sky, and perform other critically important functions. Installing the avionics takes anywhere from several days to several weeks, depending on the complexity and type of the aircraft. More than 10,000 people are involved in the aircraft assembly process, including engineers, technicians, testers, and other specialists. The production cost for a single A380 aircraft is around 445 million United States dollars, making this project one of the most expensive in the world of aviation. Just for the development of new technologies and the improvement of automation processes, Airbus spends millions of dollars every year. Every single year, more than 200,000 hydrocycles are sold all around the globe. And the overall market for this type of equipment exceeds $2.5 billion United States of America dollars. But how does a piece of composite material turn into a genuine water monster that can accelerate up to 70 miles per hour? What makes the Japanese Yamaha factory the largest hydrocycle manufacturer in the entire world? From automated hull molding to the most advanced engines and on-water testing, today we are going to unveil every secret of their production. Fasten your seatbelts because we are heading into a realm of high speeds and groundbreaking innovations. The design of hydrocycles begins with conceptual ideas and essential requirements for technical specifications. The very first stage involves identifying the target audience and the purpose of the hydrocycle. It can be a recreational model, a sports or extreme hydrocycle, or even specialized versions for fishing or rescue operations. Designers and engineers must consider not only the visual appeal, but also factors such as maneuverability, stability, top speed, comfort, and water safety. They carefully think through each detail so that the final product meets the needs of both beginners and seasoned riders. According to Statista, the global hydrocycle market by the year 2027 will grow to over $2.5 billion United States of America dollars, with an annual growth rate of 8.3%. This impressive forecast shows just how much interest hydrocycles continue to generate in different parts of the world, especially as new technology makes them more efficient, eco-friendly, and fun to ride. One of the biggest markets for hydrocycles is the United States of America, where more than half of all hydrocycles worldwide are sold. This country remains a leader in water sports development, partly because of its numerous resorts, lakes, rivers, and coastlines, which make hydrocycles immensely popular among both local residents and tourists. Hydrocycles are also well liked in Australia and Japan, where water activities are an integral part of cultural traditions, and people love to explore different forms of aquatic adventure. During the development stage, important factors include the design of the hull, which must be light yet strong and resistant to mechanical damage. For this purpose, high-quality materials such as fiberglass, composites, and aluminum are used to achieve the required rigidity without adding too much weight to the hydrocycle. Another critical consideration is the choice of engine. Most hydrocycles use internal combustion engines, although a growing number of manufacturers are experimenting with electric models, which offer cleaner emissions and produce less noise. In modern hydrocycle design, special attention is paid to innovative technologies, including digital control systems, integration of the global positioning system, and sensors for monitoring the condition of the equipment and improving navigation. These features not only make the experience more convenient for the rider, but they also boost overall safety through automatic stability control systems or engine rotation alerts. All of this simplifies the hydrocycle piloting process and makes it safer, even for first-time enthusiasts. The United States of America holds over 50% of the global hydrocycle market. Another notable trend is the rising demand for electric hydrocycles. Although they currently occupy only a small share of the market, their environmental advantages could make them a key part of the hydrocycle industry's future, since they help reduce emissions and lower noise pollution levels on the water. An essential element of design involves creating an ergonomic layout that ensures comfort during lengthy rides or races. Seats must be comfortable and provide proper support for the rider's posture, while also featuring a non-slip surface that holds up in wet conditions. Additionally, hydrocycles are equipped with various features, such as extra storage compartments, waterproof pouches, and cooling systems that help the vehicle operate at high revolutions over long periods. Developing new models also requires numerous water tests to check how the hydrocycle performs in real conditions. This process helps identify any weaknesses in the design or technical parameters, which are then corrected before the start of mass production, guaranteeing that customers receive a high-quality product. The hydrocycle development process is extremely detailed and demands meticulous attention at every phase, from designing the hull to testing the final product. Engineers, designers, and manufacturing specialists must work in close collaboration to produce equipment that is not just powerful and fast, but also safe and comfortable for users. Hydrocycles need to be easy to maneuver on the water, while also having enough durability to withstand heavy loads, water pressure, salt, ultraviolet radiation, and other environmental factors. These stringent requirements mean that the choice of materials for different hydrocycle components must be carefully evaluated to balance weight, strength, and resistance to corrosive elements. First and foremost, a key element of any hydrocycle's construction is its hull. This is one of the main parts that must be strong enough to resist mechanical damage and, at the same time, provide optimal hydrodynamic characteristics. The most common materials for hull manufacturing include fiberglass, composite substances, and aluminum. Fiberglass is selected because it offers high strength at a low weight and is resistant to corrosion, making it ideal for use in aquatic environments. In addition, it can be molded easily, allowing engineers to create sleek, aerodynamic shapes for the hydrocycle hull. Composite materials, which include polymers reinforced with fibers such as carbon or Kevlar, are even more advanced, delivering greater strength while reducing weight. They also exhibit excellent resistance to ultraviolet exposure and chemical agents like salty water solutions. By combining these materials, manufacturers can cut down on hydrocycle weight while improving speed and maneuverability, which is especially beneficial for sports-oriented models. When it comes to internal components, such as fuel tanks and cooling systems, manufacturers often rely on stainless steel or specialized plastic blends. Stainless steel is a long-lasting material that resists corrosion, making it perfect for repeated contact with water and various liquids. Plastic blends, such as high-density polyethylene, are used due to their lightness, durability against chemical and mechanical impact, and ability to function effectively for extended periods in high humidity conditions. Another crucial consideration is the choice of materials for hydrocycle engines. Lightweight yet powerful substances are essential for achieving high revolutions without sacrificing endurance. Typically, engine components are made from metal alloys, including aluminum, titanium alloys, or magnesium. These materials have low density, which helps reduce engine weight, and they have excellent thermal conductivity, which is critical for efficient cooling and overall engine performance. One well-known hydrocycle manufacturing facility is located in Japan, operated by Yamaha Motor Company, which is widely recognized as one of the leading brands in the watercraft market. Situated in the city of Iwata in Shizuoka Prefecture, this factory produces not only hydrocycles, but also other types of water transport and their engines. The Yamaha Motor Factory spans approximately 250 acres, making it one of the largest facilities in the world dedicated to water equipment production, including hydrocycles. The site specializes in manufacturing a broad range of water transport products, including diverse hydrocycle models, boats, yachts, and other motorized water vehicles. Every year, this factory turns out thousands of products, including over 60,000 hydrocycles annually, which secures Yamaha a substantial market share in the water transport sector. Thanks to the factory's expansive premises, every stage of production, from assembly to testing and packaging, can be carried out efficiently and in one location. One of the main automated lines is responsible for forming hydrocycle hulls using materials such as fiberglass and composites. This line is equipped with robotic arms that precisely shape and join individual hull components, delivering the exact design contours and a smooth exterior finish. In addition, automated welding and painting systems are used to process metal parts, such as engines and their subsystems. The line features robotic welding machines that provide accurate, high-quality welds, as well as automated painting systems that evenly coat components and offer reliable protection against corrosion. This advanced technology helps ensure the product maintains a pristine appearance and robust structure over an extended service life. The assembly lines have a real-time quality control system, which automatically identifies defects at any stage of production. This includes visual inspections using cameras and scanners capable of detecting even the smallest flaws in parts, allowing the factory to preserve the highest possible product quality. A distinctive feature of this factory is its extensive automation in the packaging and shipping phases. Once hydrocycles have passed all quality checks, they move on to automated packaging lines, where robotized systems assemble boxes and secure the hydrocycles inside transport containers. This process enhances shipping safety and streamlines logistics, ensuring that the products are delivered to customers in excellent condition and on schedule. The Yamaha factory continuously adopts the latest technologies in water equipment production. For instance, they use three-dimensional printing to create prototypes of new models, enabling faster testing and refinement of their designs. Moreover, the facility employs pioneering materials that help reduce the weight of hydrocycles, increase their corrosion resistance, and extend their service life. They also make active use of intelligent production management systems, which optimize manufacturing processes, cut down on costs, and shorten the time needed to produce each unit. As a result, the factory can expedite hydrocycle manufacturing and boost output volume, illustrating Yamaha's commitment to continuous innovation and leadership in the fast-paced world of hydrocycle development. 850 horsepower. That is the power output of the hybrid Lamborghini Revuelto. This is almost like having the force of 2 average tanks. Whenever you see a Lamborghini on the road, it is impossible not to turn your head. This is a car that shouts success and style, and it does so very loudly, thanks to its V12 engine. A Lamborghini is not merely an automobile. It is a symbol of status, luxury, and wildly high speed. However, this car is not just beautiful. Its heart is a genuine masterpiece of engineering. Shall I tell you about the engine? Lamborghini is renowned for its naturally aspirated engines that roar like a wild beast. The brand's most famous motors are the legendary V10 and V12, which provide not only insane power, but also an incredible sound that sends chills down your spine. The V12 engine was already present in the first Lamborghini 350 GT from the year 1963, and it remains the company's signature to this day. The establishment of Lamborghini was not merely a business project, it was an act of revenge. In the small town of Sant'Agata Bolognese, under the blazing sun of Emilia-Romagna, a company was born that challenged none other than Ferrari. Ferruccio Lamborghini was a successful businessman who became wealthy through the production of tractors. He owned an entire collection of sports cars, but he had problems with the Ferrari 250 GT because its clutch often broke down. One day, Lamborghini decided to express his dissatisfaction directly to Enzo Ferrari. He proposed improving the cars, but he was met with this response: "Ferruccio, you are just a farmer. You should focus on tractors and stay out of sports cars." Those words were the point of no return. Lamborghini resolved to build his own supercar that would surpass Ferrari. He hired the best engineers, including Giotto Bizzarini, the person who had developed engines for Ferrari. The team created that same legendary engine that became the heart of the first Lamborghini 350 GT. Even then, the car showed that Lamborghini was not joking around. It was faster and more comfortable than Ferrari. The first car was a success, and the company began to grow rapidly. Within only a few years came the legendary Misura, then the Countach, the Diablo, the Murcielago, and the Aventador. And now, for 60 years, Lamborghini has continued to be a symbol of status, aggression, and an engine's ferocious roar. The main Lamborghini factory covers 1,743,752 square feet. That is nearly the size of 23 soccer fields. This place is a genuine temple of speed and engineering artistry. All the critical steps in creating supercars are concentrated here. Massive pavilions equipped with ultra-modern technology merge with the craftsmanship of hand assembly, which remains an unchanging tradition of the brand. The factory includes a materials laboratory where carbon fiber is tested, paint booths where each automobile receives a perfect finish, and the exclusive ad personam division that allows clients to customize their Lamborghinis down to the finest detail. Every vehicle undergoes strict quality tests before leaving this temple of speed, bound for owners all over the world. In the year 2023, Lamborghini set a production record for the entire history of the company. 8,405 brand new cars rolled off the factory line. Every contour of the body is designed not only for aerodynamics, but also for maximum visual impact. The low profile, the aggressive front end, the sharp edges, and the massive air intakes all form the image of a wild predator ready to pounce. The signature guillotine doors on the Aventador or Revuelto models are an unforgettable sight. They lift upward. The moment you open them, you already look like a movie star. Buying a Lamborghini is not simply about money. It is about a way of life. Lamborghini owners want to stand out, be at the center of attention, and experience an adrenaline surge each time they press the gas pedal. It is no surprise that among these owners are soccer players, actors, business people, and even princes. Lamborghini has always been synonymous with exclusivity. Production is limited. Most models are released in small batches, and some appear in limited runs of 10 or 20 units. For example, the Lamborghini Centenario was produced in only 40 units, 20 coupes, and 20 roadsters. Lamborghini uses only premium materials, most of which come from the world's top suppliers. The main material is carbon fiber. Did you assume the body was made of metal? It is not. Carbon fiber is an ultra-strong yet lightweight material made up of extremely thin strands of carbon, each roughly 10 times thinner than a human hair. It is stronger than steel, but weighs several times less, making it ideal for supercars. Carbon fiber begins with polyacrylonitrile threads, which are a synthetic material similar to plastic. The fibers are heated in special furnaces with oxygen, which alters their chemical structure and makes them thermally stable. Then the fibers move into furnaces without oxygen, for instance in a nitrogen atmosphere. Under extreme temperature, they lose all inorganic components and are left as nearly pure carbon. These carbon threads are then treated to bond more effectively with polymer resins. The finished fibers are woven into fabric or laid out as ribbons. The carbon fabric is infused with resin and then shaped as needed. Lamborghini uses forged composites technology, where the fibers are arranged randomly, resulting in parts that are even lighter and stronger. The form goes into a high-temperature, high-pressure autoclave, where the composite hardens and gains extraordinary rigidity. Imagine strands thinner than a hair passing through furnaces at 3,632 degrees Fahrenheit. What comes out is a black thread that is 5 times stronger than steel, yet 7 times lighter. Instead of a conventional steel component weighing 33 pounds, Lamborghini gets a carbon substitute that weighs 6 pounds, while preserving the same strength. This material enables Lamborghini to craft bodies that are light, strong, and fast, reducing the vehicle's overall mass and boosting its aerodynamics and performance. Aluminum is sourced in Europe, especially from Italy and Germany. It is utilized for fabricating the chassis, the load-bearing body components, and various structural parts, since it is both light and strong. Suppliers deliver aluminum as sheets, profiles, or ingots. When it arrives as ingots, it is melted down and cast into blanks. Aluminum is melted in special furnaces at around 2,232 degrees Fahrenheit. The molten metal is poured into molds under high pressure. The casting solidifies in a matter of seconds and is then removed. The cast pieces are ground, excess material is trimmed off, and they undergo heat treatment to enhance their strength. Using aluminum makes the frame about 40% lighter than a steel alternative. Lamborghini's press machines can produce up to about 11,000 short tons of forming pressure. A single aluminum Aventador frame weighs a mere 504 pounds, which is essential for high speeds and maneuverability. Natural Italian leather arrives from renowned tanneries in Tuscany and Piedmont. Alcantara is sourced from a factory in Umbria for the upholstery. Carbon inserts are produced directly at Lamborghini. It may require 7 or even 8 cowhides to upholster the interior of one Lamborghini. Buyers can choose any color of leather via the Ad Personam personalization program. Lamborghini uses premium Napa leather and aniline leather, which both have a natural texture and softness. All leather sections are handcrafted to maintain exclusivity. The leather is manually cut for each part to avoid defects or unevenness. Every seam is also stitched by hand, ensuring precise quality control. Special leather threads are used for this purpose. Each piece is dyed and treated to achieve the requested appearance and texture, consistent with the client's wishes. Once every piece is ready, it is assembled and installed in the automobile. Alcantara is a high-end synthetic material that resembles suede in both look and feel. It is widely applied in the automotive sector. Alcantara is soft, matte, and holds up better to wear than genuine leather. It is also twice as light as leather, which is critical for supercars. It does not fade, retaining its color even under direct sunlight, and it is made of 68% recycled materials. The assembly process begins with preparing the vehicle body and chassis. This involves installing a foundation constructed from lightweight metals or carbon fiber, depending on the specific model. At this stage, every mainframe element is brought together, including the suspension, the exhaust system, and other key components. This step is of the utmost importance, as it lays the groundwork for everything that comes afterward. The body is assembled by hand, using specialized tools and fixtures to ensure maximum precision and minimal gaps. Once the body and chassis are complete, the next step is the installation of the engine and the transmission. The engine is the heart of a Lamborghini, and putting it in place is an exceptionally intricate process. All Lamborghini engines are built and tested separately prior to being mounted in the car. Installing the engine also requires connecting it to the cooling system, the exhaust, and the vehicle's electronics. After this, the gearbox and the transmission system are fitted, allowing the engine's power to be transferred to the wheels. During this phase, all of the vehicle's critical systems are also fine-tuned, including the suspension and braking systems. The following stage involves installing the car's interior parts. This includes the seats, the instrument panels, the door trim, and the steering wheel. All these elements are made by hand using superior quality leather or Alcantara, in the case of sportier versions, along with other exclusive materials. Every piece is finished with meticulous attention to detail, creating a truly unique cabin. For instance, Lamborghini seats are crafted by hand to accommodate every curve of both driver and passenger, providing outstanding comfort. The steering wheel is also handmade and can feature a personalized design, according to the client's preferences. Once the principal interior components are set, the car moves on to the phase dedicated to connecting the electronic systems. Lamborghini cars are noted for their cutting-edge technology, so they come equipped with intricate infotainment setups, navigation, touchscreens, and safety systems. All wires and electronic parts must be hooked up with extreme accuracy to avoid errors or malfunctions. This process can take several hours and calls for highly qualified technicians who precisely follow each component's wiring diagrams. Having finished the physical assembly of the automobile, Lamborghini proceeds with the testing stage. Each vehicle goes through a detailed evaluation on special test stands, where every function and system is checked, ranging from the engine and transmission to the brakes and suspension. This helps detect any faults or issues before the car reaches the end buyer. One of the most vital segments of testing is assessing the car's performance dynamics on the track. Here, the automobile's characteristics at high speeds are evaluated, along with its maneuverability, braking force, and stability when cornering and accelerating. Once all tests have been completed, the car returns to the assembly hall for a final inspection. If all systems operate correctly, the vehicle undergoes one last quality assessment. After this, it receives finishing touches, such as body polishing and a thorough check of every surface for paint defects. At Lamborghini, each car has its own special color, chosen during the production phase. After this, it receives finishing touches, such as body polishing and a thorough check of every surface for paint defects. At Lamborghini, each car has its own special color, chosen during the production phase. Imagine this. Every year, more than 50 million drums are made around the world. But have you ever wondered how a piece of wood becomes a powerful instrument that sets the rhythm for music? From ancient shamanic rituals to modern rock arenas, drums have always been the heart of sound. To create the perfect drum, wood is dried for years, metal parts are crafted with jewelry-like precision, and membranes undergo special treatments. Today, we're going inside this process, step by step, from the lumber mill right onto the stage. The drum is one of the oldest musical instruments in the world. Its history stretches back at least 7,000 years, perhaps even more. The earliest drums were simple, animal skins stretched over wooden or clay bases. Over time, they evolved into the complex structures made from various materials that we see today. The oldest drums found by archaeologists date back to 5,000 years before Christ. They have been discovered in Africa, Mesopotamia, China, and Egypt. These early drums featured clay or wooden bodies with animal skin membranes stretched with ropes or glued on with resin. In shamanic rituals and religious ceremonies, drums were used to communicate with spirits. In ancient China and Egypt, drums coordinated armies on battlefields. In some African tribes, drums were even used to send messages over long distances. In the Middle Ages, drums became popular in Europe thanks to the Arabs, who brought them through Spain during the Muslim conquests. During this period, drums became integral to military music and later orchestras. A drum isn't just a chunk of wood or metal. Every part matters. The shell, the membrane, the hoops, bolts, and even the drumsticks. All these elements are crafted from carefully selected materials, and each affects how the instrument sounds. Wood used for drum shells must be properly dried, processed, assembled, and finished with lacquer. Metal parts are cast, polished, and protected against corrosion. The process is more complex than it first appears. Let's dive deeper into these details. Wooden drums have a special warmth to their sound. But as we said before, creating such a shell first requires carefully selecting, preparing, and drying the wood. The most popular choice for drum shells is maple. It produces a warm, balanced tone with excellent lows, mids, and highs, making it a staple in most studio and live drums. Birch provides a bright, aggressive sound, boosting the highs and lows, perfect for rock, metal, and live performances. Mahogany offers a deep, bass-rich sound with mellow highs, famously used in vintage drums from the 1950s and 1960s. Bobinga, a dense African hardwood, delivers a darker, powerful tone with great attack. More expensive, it's reserved for premium models. Oak, harder than maple, provides an exceptionally loud, penetrating sound ideal for live settings. Simply cutting down a tree and slicing it into boards is just the beginning. The tree must be harvested in a specific season, usually winter, when it contains the least moisture. Logs without cracks or knots are chosen. Freshly cut wood can have up to 60% moisture. First, the wood air dries outdoors for several months or even years. Then it undergoes kiln drying, reducing moisture content to between 8 and 12%. Next, boards are sliced into thin layers called plies, glued together under high pressure. The thickness of these wooden plies typically ranges from 0.024 inches to 0.118 inches. To produce uniform, thin layers without excess waste, several methods are used. Rotary cutting involves mounting logs onto special machines that spin them while blades peel thin, continuous wood strips, typically for budget drums. Bandsawing uses a flexible, continuous saw blade, moving in a loop to cut logs into thin plies. This method provides more precise cuts than rotary peeling, and preserves the wood grain better, although it creates more waste. For high-end drums showcasing exotic wood grains, manufacturers employ veneer slicing. Logs or boards are fixed, then moved against a sharp blade to shave off thin sheets. Laser cutting is the least common method. Premium drums sometimes feature solid wood shells, providing unique tonal qualities. But today, we're not focusing on those. Let us know in the comments if you'd like a separate video dedicated to that topic. First, the plies are coated with special glue, then stacked, forming a multi-layered structure. The number of layers typically varies from 4 to 20, depending on the desired shell thickness. Next, this stack is placed into specialized molds, bending the wood into a perfectly round cylinder. Even pressure is crucial to prevent defects and air bubbles in the glue. Afterward, the shells dry for several hours or even days. Once the glue hardens, shells are removed, edges trimmed, sanded, and drilled for hardware. This method is economical and allows manufacturers to experiment with combinations of wood types to influence sound characteristics. Polishing and applying finishing coatings is primarily manual work, especially for high-quality or custom drums. Shell surfaces are carefully sanded, removing all irregularities. Sanding happens either by hand or machine, progressing from coarse to extremely fine abrasives, usually from 120 to 400 grit. For glossy lacquer finishes, manufacturers may first apply primer to prevent excessive absorption by wood pores. Oil or wax finishes are rubbed in manually using soft cloths or brushes, penetrating deeply into the wood pores, protecting from moisture and enhancing the natural color. Lacquer is sprayed in several thin layers, drying completely between each coat. This process is performed by skilled artisans manually or by automated equipment in large factories. After drying, shells receive a final polishing to achieve the desired gloss, ranging from matte to mirror-like shine. In large companies like Pearl or Yamaha, producing hundreds of drums, lacquer is applied automatically. Still, final finishing always occurs by hand, since even the best machines cannot match human precision. Boutique manufacturers such as Cravioto, Brady, or Noble & Cooley finish every shell entirely by hand, making each drum unique and even more expensive. Even wooden drum shells have numerous metal parts: hoops, tension rods, and grommets. Hoops are typically chrome-plated steel, brass, aluminum, or even wood. Tension rods are commonly stainless steel or brass. Grommets are small metal inserts reinforcing the drilled holes in the shell. How are metal parts produced? Metal is melted at high temperatures, then cast or machined into required shapes. These parts are sanded and polished, removing roughness, then coated with protective layers like chrome or nickel to prevent rust. Historically, drums featured animal skins: cow, goat, or buffalo. Nowadays, synthetic plastics are more common due to their stability, durability, and weather resistance. Natural animal skin, being organic, expands and contracts with humidity and temperature changes. Moisture makes skins softer and sounds duller, whereas dry conditions cause them to shrink and crack. Synthetic materials maintain consistent tension regardless of weather. Once tuned, synthetic drumheads remain stable until manually adjusted. Drumhead materials, whether skins or plastic, are cut into circular pieces, treated chemically for flexibility, then pressed and stretched onto metal hoops. Preparing animal skins is truly spectacular. Inside large workshops, air smells of smoke, salt, and something sharp. Huge wooden vats line the walls, holding pieces of skin that visibly change color. This isn't mere soaking. It's true alchemy transforming tough, uneven hides into perfect drumheads. Initially, skins soak in large vats containing lime solutions, softening them and removing hair. After several hours or days, skins become lighter but still coarse. Next, they're treated with tanning substances, penetrating their structure on a molecular level. Vats emit steam. The aromas of wood, metal, and rawhide blend in the air. To avoid excessive stiffness, skins are stretched onto large wooden frames. Craftsmen stretch the skins manually, feeling thickness with their fingers. Sometimes steam is used, filling the workshop with thick vapor as skins are warmed before final treatment. Lastly, skins are rubbed with special mixtures: oils, waxes, sometimes herbal extracts. This keeps them flexible yet strong. In some regions, they're even smoked, imparting a light, smoky scent and improved water resistance. Even the best drum won't sound great without proper drumsticks. These are also crafted from carefully selected wood. Wood, typically hickory, maple, or oak, is sawn into blanks and air-dried naturally. But this takes time, so kilns usually speed the process, carefully controlling temperature and humidity, aiming for moisture content of 6 to 8%. Correct moisture levels are critical. Too moist, sticks warp. Too dry, they become brittle. Dried blanks are shaped on high-speed lathes. Each stick must have identical diameters. Otherwise, sticks within pairs produce different sounds. Simply turning a round stick isn't enough. Tip shape, taper in the middle, and weight distribution define how sticks sound when striking drums. High-speed lathes achieve precision within thousandths of an inch to ensure consistent quality. Every year, we produce approximately 101 million short tons of textile waste, and more than half of that trash simply rots in landfills. But what if we could turn it into something useful? Imagine this: your favorite t-shirt, a stylish blazer, or even designer sneakers, all made from plastic bottles. Yes, fashion is already changing, and brands are turning waste into trendy clothing. How exactly does plastic become fabric? Why are large companies already earning millions from this? And does such clothing truly save the environment? Let us figure it out. Every year around the world, approximately 101 million short tons of textile waste are produced, of which only 15% is recycled, while 57% ends up in landfills. We need to do something about that, right? It might sound like science fiction, but in fact, plastic can be easily recycled into fabric. Let us start with the fact that most of the textiles we wear every day consist of synthetic fibers, such as polyester. Here is something interesting. Polyester is nothing more than plastic. Yes, you understood that correctly. Plastic bottles or other plastic waste can be turned into fibers that are then used to make fabrics. The process looks like this. Old plastic bottles, plastic containers, or even damaged plastic items are collected, washed, cut into small pieces, and then these pieces are melted down into new plastic fibers. These fibers are then woven into fabric that, in terms of its characteristics, is almost no different from traditional materials like cotton or wool. Now imagine this. It is not just a technological marvel, but also a chance to reduce the amount of plastic that ends up in nature. This usually happens in the following way. Plastic is sorted by type of plastic, most frequently polyethylene terephthalate, and by color. Clean and transparent plastic is more valuable because it is easier to obtain high-quality raw material from it. After that, the waste is washed in special baths to remove any remaining beverages, glue, and labels. Then, special industrial shredders equipped with sharp blades cut the plastic into uniform fragments. Sometimes water cooling is used for this purpose, in order to avoid overheating the material. The smaller the plastic is shredded, the easier it is to melt and clean it from impurities. Next, the shredded plastic is heated to about 932 degrees Fahrenheit until it becomes a viscous liquid mass. Then, this melted mass goes through special filters to remove any remaining contaminants. After that, it is extruded through fine nozzles, creating thread-like fibers. These fibers are cooled by a stream of air or water, after which they are twisted into yarn that becomes the basis for textile materials. It is impossible not to notice that fashion is now moving towards sustainability. All those popular brands we know and love, such as Adidas, Patagonia, and Stella McCartney, are increasingly using recycled plastic in their collections. However, let us pause here. What makes this plastic so popular? Environmental friendliness. As we know, plastic is one of the biggest enemies of the environment. Every year, millions of short tons of plastic end up in landfills or in oceans. But through recycling, we can reduce that impact by turning plastic waste into useful materials. And this is not just one of the eco-initiatives of brands, it is a real shift in the industry. Interestingly, some designers and brands already use textiles made from recycled plastic, not only for environmental benefits, but also for the unique look. In particular, materials made of plastic fibers can have very intriguing texture and sheen, which gives clothing a bit of an innovative and futuristic appearance. Imagine a t-shirt that is not only made from plastic, but also has a striking texture that reminds us of the future. Research shows that reusing textiles can save up to 8 short tons of carbon dioxide and approximately 164 gigajoules of energy for every short ton of textile waste. Converting that to American measures, 164 gigajoules is about 155 million British thermal units. Recycling textiles saves 5 6/10 short tons of carbon and about 116 gigajoules of energy per short ton. which is around 110 million British thermal units. That is a considerable difference on a global scale. Technology. Fabrics made from recycled plastic can be just as comfortable and stylish as regular fabrics. They even have certain advantages. They are water repellent, resistant to fading, and they hold up well to wear and tear. Moreover, if these fabrics are processed correctly, they can be made soft and pleasant to the touch. And here, we should remember another point: microplastic that can enter water through recycled fabrics. When we wash clothes, especially items made from synthetic materials, microscopic plastic particles can get into the water. However, some brands are already working on solutions to minimize this impact. For example, they use special technologies to reduce the release of microplastic during washing, or they create materials that are less prone to this. Innovation. However, it is worth noting that this is not just a trend. It is an innovation. Instead of continuing to produce more plastic, brands are finding ways to use what already exists. This opens up new possibilities for the fashion industry. For instance, one of the most fascinating technologies is recycling ocean plastic. The same plastic that is flooding our oceans can also be turned into clothing. For example, the company Parley for the Oceans creates materials from plastic collected from the oceans. This not only helps decrease the amount of plastic in the water, but also becomes the foundation for eco-friendly collections by brands such as Adidas. That is a whole different story, right? If you think that recycled plastic is something only for sportswear or accessories, you are mistaken. Imagine a stylish coat or an elegant dress made from material that was once a plastic bottle. These recycled plastic fabrics make their way onto the runways of major fashion shows and become part of refined collections. One of the most interesting examples is the Stella McCartney collection, which recently introduced a clothing line made from fabrics produced from recycled plastic bottles. And of course, you will not find any trace that these fabrics were ever anything else. They look and feel completely sophisticated. This is not merely about disposal. It is about creating genuine art out of what we used to throw away. Speaking of scale, some countries, such as the Netherlands or Sweden, have become true leaders in plastic recycling. There are even specialized factories there that transform plastic waste into textile, which then becomes part of both sports and everyday clothing. It is an entirely new approach to waste processing that not only helps preserve resources, but also creates new jobs. It turns out that the process of recycling plastic into textile not only saves the planet, but also has significant economic potential. Many small startups around the world have begun to build business models based on the collection, recycling, and resale of plastic waste in the form of clothing. Such businesses often collaborate with local communities, involving them in collecting and recycling waste, which creates new jobs and stimulates the economy at a local level. Technologies of three-dimensional printing also use recycled plastic to create fabrics. Some companies have already started making textile materials by utilizing plastic waste through three-dimensional printing. This allows the creation of entirely new textures and shapes, as well as optimizing the clothing manufacturing process. Imagine clothing that is literally printed using plastic. In recent years, the so-called smart fabrics have also been gaining popularity in the textile industry. Materials that can change their properties depending on the surrounding conditions. Recycled plastic has a role here as well. Some brands are experimenting with integrating nanotechnologies into fabrics made from recycled plastic, enabling the creation of textiles that respond to temperature or moisture, making clothing more functional and comfortable. It sounds like something from a fantasy, but there are already materials made from recycled plastic that can self-clean. They have special coatings that allow the fabric to repel dirt and water. This technology can change the rules of the game in terms of durability and convenience, because clothing made of such fabrics would require much less washing. Another exciting direction involves fabrics that alter their appearance depending on how a person interacts with them. For example, fabrics that respond to body heat or change color during movement. All of these innovations can be created using recycled plastic, opening up new opportunities in fashion. One more interesting aspect is the recycling of plastic into artificial leather. Some innovative brands have already started making eco-friendly artificial leather out of recycled plastic waste. Such leather can be used to manufacture bags, footwear, and even outerwear. This offers a material that resembles genuine leather, but without the use of animal products and with a smaller environmental impact. Here is the thing. Today's youth is a generation that is becoming increasingly aware of environmental issues. You are no longer just buying clothing. You are buying clothing that tells a story. You are buying not just fabric, but a certain idea. A future that can be more sustainable and clean. And when you wear clothing made from recycled plastic, you are not merely shopping. You are joining the change. You are becoming a part of this large movement. Of course, there are questions about the cost, quality, and availability of such materials. But do you know what? It is only a matter of time. With the advancement of technology and the growth in demand for eco-friendly products, these fabrics will become even more affordable. And that is great, because each of us can contribute to improving the situation. Perhaps in a few years, we will only wear clothing made from recycled material. And, to be honest, that does not seem so fantastic. It might become the norm, rather than the exception. And who knows, maybe in the future, even your favorite brand will use plastic waste to create new trendy items. Yes, it sounds like science, but science and fashion can accomplish many wonders together. So the next time you are choosing what to wear, think about this. Maybe it is another step toward a better world. And if plastic waste can become part of your style, then why not? Every single day, more than 15 billion cigarettes are produced worldwide. That is 173,000 every single second. But how does an ordinary tobacco leaf transform into a cigarette? What happens behind the closed doors of factories, where massive machines work non-stop to roll out thousands of packs every single hour? Today, we will reveal all the secrets, from enormous tobacco plantations to high-tech packaging lines. And you will be shocked at the hidden processes behind this industry. Stick around until the end so you do not miss the most fascinating details. The very first tobacco factory in Europe was established in Seville, Spain, in the year 1728. For over a century, this factory supplied Europe with cigars, generating substantial profits for the Spanish treasury. Today, Europe is home to major tobacco companies such as British American Tobacco, Philip Morris International, and Imperial Brands. For instance, in the year 2024, Imperial Brands reported an operating profit of £3.5 billion British pounds, which was 4.5% higher than the previous year. This growth was driven by a 26% increase in revenue from alternative products, such as electronic cigarettes and nicotine pouches. Growing tobacco requires a specific climate, as this plant thrives in warm weather and fertile soil. The primary regions for tobacco cultivation include North and South America, Africa, Southeast Asia, and Europe. The leading countries in tobacco production are Brazil, China, India, the United States of America, Zimbabwe, Turkey, and Italy. China is the world's top tobacco producer, cultivating more than 2 million metric tons of tobacco leaves annually, which accounts for over 40% of global production. The key tobacco growing regions in China are Yunnan, Guizhou, Hunan, and Sichuan provinces. India produces approximately 800,000 metric tons of tobacco per year, primarily in the states of Andhra Pradesh, Telangana, and Karnataka. Tobacco seeds are sown in the spring, and the leaves are harvested several months later. This process can take several weeks since each layer of leaves is collected separately. After harvesting, the leaves are transported to specialized facilities, where they undergo fermentation and drying. The most common drying methods include air curing, fire curing, or sun curing, depending on the type of tobacco. For instance, Virginia tobacco is fire cured, meaning the leaves are hung in curing barns where the temperature is carefully maintained using heated air. This process lasts about 7 to 10 days and gives the leaves a golden color and a mildly sweet aroma. Burley tobacco, on the other hand, is air cured in shaded barns for an entire month, resulting in a more intense and dry flavor. After drying, the tobacco leaves go through fermentation, which helps reduce nicotine levels and remove excessive bitterness. This fermentation process can last several months. A large portion of the tobacco used for cigarette production in Europe is imported from Brazil, Zimbabwe, China, and the United States of America. Some countries, such as Italy, Greece, and Turkey, cultivate their own tobacco, which is also processed in local factories. Every batch of tobacco arriving at production facilities undergoes strict quality control, where factors like moisture content, color, and nicotine levels are analyzed. The process begins with the initial treatment of tobacco leaves. First, the leaves are sorted by quality and type, with damaged or unsuitable parts removed. On average, each cigarette contains approximately 1 gram of tobacco, meaning that large factories process hundreds of metric tons of raw materials daily. After sorting, the tobacco is processed in manufacturing plants, where machines take over most of the work. The leaves are first shredded into fine fibers. Machines meticulously control the size of these shredded pieces to ensure uniformity. Then, the tobacco undergoes steam treatment to increase its elasticity and improve storage conditions. Various flavorings and stabilizing agents are added to regulate moisture levels and enhance taste characteristics. Typically, cigarette blends include a mix of different tobacco varieties to achieve the desired flavor and strength. The next stage is cigarette formation. Production lines are equipped with specialized machines capable of rolling out more than 20,000 cigarettes per minute. These automated lines operate with incredible speed and precision. The process begins with shredded tobacco being evenly distributed onto a conveyor belt. Next to this belt, a continuous strip of cigarette paper is unrolled. The machine wraps the tobacco in the paper, forming an uninterrupted tube that resembles a long roll. This roll moves along the belt at high speed, and special cutting blades then slice it into individual cigarettes, each approximately 3 inches long. Filter production is a separate process that begins with a primary material, usually acetate fiber. This synthetic polymer is derived from cellulose, which comes from wood pulp. The fibers are treated with special chemicals to give them the required structure, after which they are pressed and formed into long strips. To bind the fibers, a plasticizer called triacetin is used, ensuring the filter maintains its shape. These long strips are rolled into cylindrical blanks, which can be several feet long. They are then cut into smaller sections that match the required filter length. On the production line, these filters are fed into a specialized mechanism that wraps them in a thin paper layer to reinforce their structure. A standard filter can weigh between 10 and 20 grams, depending on the type, and its volume can range from 1 to 3 milliliters. In large-scale manufacturing, several metric tons of acetate fiber may be processed daily, with the total volume of filters produced reaching hundreds of thousands of liters. Next, the filters are attached to the tobacco rod. This is done using wrapping paper that is bonded with food-grade adhesive to create a strong connection between the filter and the tobacco-filled portion. In the bonding area, the wrapping paper passes through a roller that evenly applies the adhesive to its surface. The filter and the tobacco rod are then precisely aligned and merged using a specialized mechanism. The wrapping paper is tightly wound around the connection point and firmly pressed to ensure a secure bond. This process happens in a fraction of a second, and each minute, the machine can attach hundreds of filters to tobacco rods. Throughout production, the total amount of adhesive used can reach several dozen kilograms per shift, while the length of tobacco rods passing through the equipment is measured in hundreds of yards. Once assembled, the cigarettes move along the conveyor to the inspection section, where the strength of the bonds, uniformity of the wrapping, and adherence to standard dimensions are checked. Special scanners and weight sensors examine each cigarette to detect any defects, such as hollow spots, uneven tobacco distribution, or damaged paper. Any defective items are automatically removed from the line. Another crucial step is the application of tracking codes on each cigarette or filter, ensuring full traceability throughout the production cycle. This is done with high-precision laser markers that do not damage the paper. Finished products are then cut to final lengths if needed before reaching the packaging section, where they are grouped into packs of 20 and wrapped in foil. Once cigarettes are paired with filters and pass quality control, they move to the packaging stage. First, the cigarettes are aligned on the conveyor, forming groups based on the intended pack size. A standard pack typically contains 20 cigarettes. although there are variations with 10 or 25 pieces. Once grouped, the cigarettes are wrapped in an inner lining made of foil paper, or thin aluminum foil, to maintain freshness and prevent drying. They are then automatically placed into cardboard boxes, which arrive via a separate conveyor. These boxes are made from thick cardboard that is pre-cut, folded, and glued using high-speed machinery. The packs then pass through a wrapping mechanism, which seals them in a thin, transparent film. This film includes a perforated strip for easy opening. At this stage, excise stamps and barcodes are printed. On average, a single packaging line can process about 15,000 packs per hour. Completed packs are arranged into blocks of multiple packs, usually 10 per block. These blocks are further wrapped in film or packed into cardboard boxes before being placed onto pallets for transportation. Large cartons can hold up to 500 packs each. The boxed products are stored in factory warehouses until they are shipped to distributor warehouses. From there, cigarettes are sent to stores, supermarkets, and specialized kiosks. Every day, dozens of trucks leave major tobacco factories, delivering millions of cigarettes to distributors and retail locations. The entire journey, from manufacturing to store shelves, can take anywhere from a few days to several weeks, depending on logistics and market demand. At large tobacco factories, machines operate continuously across multiple shifts. In a single workday, one of these machines can produce several million cigarettes. Modern cigarette manufacturing is characterized by a high level of automation, minimal human involvement in production, and rigorous quality control at every stage. Factories are equipped with air quality management systems to maintain stable humidity and temperature, which are crucial for preserving tobacco properties. A typical tobacco factory can produce up to 200 million cigarettes per day, amounting to thousands of metric tons of finished products each month. Imagine this. Every single year, all around the world, over 70 million automobiles are manufactured, and each one of them demands high-technology glass. From the broken flask with nitrocellulose that accidentally revealed laminated glass, to the powerful hydrophobic coatings, the history of this material is truly astonishing. Today, we are going to learn how glass becomes ultra-strong, safe, and prepared to protect us from wind, rain, and the dangers of the road. Please get ready for a journey into the realm of advanced modern technology. Thousands of short tons of glass scrap are recycled in order to create crystal clear windows for automobiles. It is not only about safety, but also about saving precious resources. And that is just the beginning. The history of automobile glass production is closely linked to the development of the automobile industry, which emerged in the late 19th century. The glass used in today's automobiles has undergone a long path of improvements that have made it safer, stronger, and more functional. When the very first automobiles began to appear, they were initially not equipped with any glass at all. The open body design offered only partial protection to passengers, while dust, wind, insects, and other hazards made traveling extremely uncomfortable. Later on, when automobiles became faster, the need for driver and passenger protection emerged. Windshields were first made from ordinary window glass, which, although it provided some degree of protection, had a serious drawback. In accidents, it would shatter into large, sharp fragments that resulted in numerous injuries. The first groundbreaking discovery in the field of automobile glass was the creation of laminated glass. This happened by chance. In 1903, a French chemist named Edouard Benedictus accidentally dropped a flask coated with nitrocellulose. The glass cracked but stayed in one piece, thanks to the thin layer of plastic. This accident inspired the scientist to develop a multi-layered glass, which later became the basis for triplex. By the 1910s, laminated glass was already being used in premium class automobiles. Its construction consisted of 2 layers of glass with a thin, transparent film in between them. In the event of impact, the glass did not scatter, and cracks remained on the film. In the 1920s, laminated glass began to be widely used in the production of windshields. Its main advantage was increased safety. Even in serious accidents, the fragments did not fly apart, but remained embedded in the polymer layer. The next stage in the evolution of automobile glass arrived in the 1930s. when the technology for making tempered glass was patented. This material was produced by heating the glass to high temperatures followed by a rapid cooling. As a result of such a process, the glass became stronger, and upon breaking, it would fracture into small pieces with dull edges, minimizing injuries. By the middle of the 20th century, tempered glass was being used for the side and rear windows of automobiles. It was less expensive to manufacture compared to triplex and provided a sufficient level of safety for those parts of the vehicle. In the 1950s and 1960s, automobile glass became even more advanced thanks to ongoing technological progress. During this time, several important changes took place. Improvement of triplex. The development of new polymer films made laminated glass more transparent, resistant to ultraviolet radiation, and more durable. Mass production. The automation of manufacturing processes drove down the cost of automobile glass, making it more affordable for a wide range of consumers. Coatings for sun protection. Special coatings that blocked ultraviolet rays and reduced the heating of the automobile cabin were used for the first time. One of the most significant technological breakthroughs in glass production was the invention of the float method in 1959. This technology, developed by the British company Pilkington, enabled the manufacturing of perfectly smooth glass by allowing molten glass to spread across the surface of molten tin. Through this method, the glass became more uniform, stronger, and better suited to mass production. Even today, the float method remains the foundation of automobile glass manufacturing, ensuring precise dimensions, a smooth surface, and high quality. In the second half of the 20th century, automobile glass underwent even more changes aimed at improving both safety and comfort. In the 1960s, heating filaments began to be installed in the rear window of automobiles, preventing condensation and freezing. In the 1980s, glass was introduced with special metallic coatings that reflected sunlight and reduced heat buildup inside the vehicle. Glass with ultraviolet protection. With the introduction of new technologies, automobile glass began providing virtually complete protection from harmful ultraviolet radiation. And now, we enter the modern period of automobile glass production, which we will discuss at this very moment. We shall start with the glass used in automobiles. Automobile glass is divided into several types, depending on its purpose and manufacturing technology. Windshield. This is usually multi-layered glass composed of two sheets of glass with a polymer film between them. This design ensures that, if damaged, the glass does not break into sharp fragments. Side and rear glass. Most often, this is tempered glass, which, upon impact, fractures into small, blunt-edged pieces that reduce the risk of injury. Panoramic roofs, or other special types of glass, often use laminated or tempered glass with specialized coatings for protection against ultraviolet radiation. The main components of glass are natural materials, which are mixed in certain proportions to achieve the desired properties. Quartz sand is the principal element in glass, giving it transparency. It must be extremely pure and contain minimal impurities. Soda is added to lower the melting temperature of glass. Lime improves the mechanical durability and chemical characteristics of glass. Additional additives. These are used to adjust color, transparency, resistance to ultraviolet light, and other properties. The raw materials are cleaned, dried, and ground to a uniform state. It is crucial to eliminate as many impurities as possible, as they can affect the quality of the glass. After preparation, the raw mixture is poured into special furnaces for melting. This stage includes a few important steps, so let us review them together. Melting temperature. To create molten glass, a temperature of about 2,732 degrees Fahrenheit is used. Throughout the melting process, the raw materials transform into a uniform, viscous liquid. Homogenization. The molten glass is stirred to distribute components evenly. This is important for preventing air bubbles or other irregularities in the finished product. The furnaces for melting glass are equipped with modern systems for temperature control and process automation, which guarantee the high quality of the final product. After melting, the molten glass proceeds to the forming stage, most commonly performed using the float method in modern manufacturing. Feeding the molten glass. The liquid glass flows from the furnace onto a bath of molten tin. Due to the high density of tin, the molten glass spreads out uniformly across its surface. Under its own weight, the glass forms a perfectly even and smooth surface. Gradually lowering the temperature makes the glass grow solid. By the time it leaves the tin bath, it is ready for further processing. The float method allows the production of glass sheets with precise geometric parameters and a very high quality finish. Once it is cooled, the sheets of glass are cut to the sizes required for automobile manufacturing. Automated cutting machines ensure accuracy, and to prevent chips or cracks, the edges of the glass are polished. Every sheet is checked for defects, such as micro cracks, bubbles, or other damage. Next, to ensure the strength and safety of automobile glass, it undergoes the process of tempering. The glass is heated to a temperature of around 1,112 degrees Fahrenheit. Then the surface is quickly cooled by air jets, while the inner layers cool more slowly. As a result, stress is created, which greatly increases impact resistance. Tempered glass, when broken, shatters into small, safer fragments, minimizing the risk of injuries. After that, for the windshield, a triplex construction is used, which is a combination of glass and polymer film. Its fabrication involves several steps. Layer bonding: a polymer film is placed between two sheets of glass. The construction is placed into a vacuum press to remove air bubbles. Then the glass is heated in an autoclave to 284 degrees Fahrenheit under high pressure, ensuring a strong bond between the layers. Triplex has high impact resistance, and if damaged, the fragments stay attached to the polymer film, thus providing safety for the driver and passengers. Afterward, to enhance the properties of automobile glass, various coatings are applied. Anti-glare coatings reduce glare from the sun or from other vehicles' headlights. Ultraviolet protection: special layers block harmful ultraviolet radiation. Hydrophobic coatings allow water to bead and roll off the glass surface. Heating elements: thin heating filaments can be embedded in the windshield, making it easier to remove ice or condensation. To achieve the required shape, special thermoforming equipment is employed. The glass is heated to a temperature at which it becomes pliable, and it is then molded according to specified parameters. And here we arrive at the final stage. During this stage, each piece undergoes a thorough inspection. The transparency is tested, and any defects are identified. Next, the glass is tested for impact resistance and durability under load, compliance with standards, the accuracy of dimensions, the shape, and other parameters are verified. Then the finished automobile glass is packaged in a manner that prevents damage during transportation. It is delivered to automobile factories or service centers, where it is installed in vehicles. The production of automobile glass is a high-technology process that brings together physics, chemistry, and engineering. Thanks to advanced technologies and strict quality control standards, automobile glass ensures safety, comfort, and longevity. And just imagine how many stages automobile glass must go through so that we can watch over road safety and admire wonderful vistas along the way. I find it remarkable. Do you also think so? Every single day, at the Lockheed Martin factory in Fort Worth, Texas, fighter jets roll off the production line, ready to dominate the skies. This is where the legendary F-16 Fighting Falcon is assembled, each one a true engineering marvel. In just 52 days, hundreds of specialists, robotic systems, and thousands of components come together to create a combat machine capable of reaching speeds of 1,500 miles per hour. How is this steel predator built? I visited the factory and saw it all with my own eyes. Ready to dive into the heart of aircraft manufacturing? Buckle up, we are taking off. At the massive Lockheed Martin factory in Fort Worth, Texas, the day begins with the roar of machinery. Gets the adrenaline pumping, right? My heart is racing. Here, in the heart of aerospace engineering, one of the most famous fighter jets in the world, the F-16 Fighting Falcon, is brought to life. But the process of building each F-16 begins long before the first part arrives at the factory. Engineers at Lockheed Martin start by working with 3D modeling systems using CATIA V5 and Siemens NX software. A digital twin of the aircraft is created to test virtual aerodynamics, simulate material strength, and optimize the placement of cables, pipelines, and electronic systems. After that, supercomputers run numerous simulations to predict how the F-16 will perform at different speeds, in combat maneuvers, or under extreme temperatures. To test the strength of the structure, prototypes of key components, such as the wings, nose section, and tail, are built and subjected to rigorous lab tests. They undergo vibration-resistant simulations to mimic turbulence, as well as extreme temperature exposure, heating up to 302 degrees and cooling down to minus 76 degrees Fahrenheit. And let's not forget impact resistance tests, like simulating a bird strike at 559 miles per hour. You love crash tests too, right? It is thrilling. Meanwhile, a separate team works on the cockpit. Test pilots evaluate the ergonomics of the instruments, the positioning of the HUD display, and the ease of control. As for the materials, supply issues are never a concern. Lockheed Martin signs contracts 2 to 3 years in advance. The standard material set includes aluminum and titanium alloys from Alcoa and Timet, which form the fuselage structure, composite materials from Toray and Hexil, used for wings, fairings, and radar-absorbing elements. Aerospace electronic systems, including radars, avionics, and targeting systems, are provided by Northrop Grumman and Raytheon. In the morning, the factory floor at Lockheed Martin has a quiet but focused atmosphere. This is not just manufacturing. This is where fighter jets that will rule the skies are born. Workers are at their stations. Some are prepping riveting guns. Others are reviewing blueprints, while some are operating laser measuring systems. Today, another F-16 Fighting Falcon is being assembled, and everything must be flawless. As you might have guessed, the factory follows a modular approach. Instead of building an entire jet in one place, it is assembled in sections before being joined together. In one of the workshops, the aluminum cockpit frame is already complete. Nearby tables hold avionics instruments, HUD displays, and computer system modules. Workers in white gloves carefully install them into compartments. The ejection seat mount is fitted, and a 12mm thick bulletproof canopy glass is installed, capable of withstanding a 13mm bullet impact. 12.5 miles of wiring are laid out, connecting sensors, displays, and control systems. Meanwhile, the central fuselage section is being assembled, the area that houses the fuel tanks, landing gear, and wing mounting points. A large aluminum frame is secured with 40,000 rivets installed by automated riveting robots. Fuel tanks with a total capacity of 845 gallons are integrated into the structure. The landing gear, capable of handling loads up to 44,000 pounds, is installed and tested. Workers meticulously check the tanks for leaks by filling them with a special gas and inspecting for any seepage. In the adjacent workshop, the tail section takes shape. It is welded together using titanium and composite panels, with an engine mount already in place, designed to withstand temperatures exceeding 2,192 degrees Fahrenheit. The elevator and rudder are then installed, followed by a check on the emergency braking mechanism. A specialized team handles this section since the tail not only controls flight, but also maintains the jet's overall balance. The wings are assembled in a dedicated section. Hydraulic mechanisms for controlling flaps and ailerons are installed, along with hardpoints for weapons. The composite wing surfaces undergo ultrasonic testing for defects. If even one layer of carbon fiber is improperly placed, the wing could deform under combat stress. So there is zero tolerance for errors. Once all modules pass rigorous inspections, they are transported to the final assembly line. The final assembly line is a massive hangar stretching 437 yards long, where hundreds of specialists work in precise coordination. Everything follows a strict schedule. Any delay in one step can impact the entire process. The central fuselage is lifted by a specialized crane and aligned using lasers. First, the cockpit is attached, followed by the tail section. Engineers use high-strength titanium bolts capable of withstanding loads of approximately 88,180 pounds. Once the primary structure is complete, it is time to attach the wings, which are secured with reinforced titanium joints to ensure structural rigidity. Engineers meticulously check the alignment angles to ensure the error margin does not exceed allowable limits. After assembling the airframe, one of the most critical moments arrives: the installation of the jet engine. It is transported in a specialized container and lifted into the tail section using a hydraulic hoist. Technicians carefully connect all systems: fuel lines, hydraulic and electrical cables, and the afterburner system that enables supersonic flight. Once installed, a dry test run is conducted to verify its operation without fuel ignition. The onboard computer, pilot displays, weapons control systems, and the ANAPG-83 radar, capable of detecting targets at a range of 100 miles, are then integrated. Before the first flight, the F-16 receives anti-corrosion treatment, paint, and stealth coating. As a kid, my best friend was obsessed with origami. She was into everything from Eastern culture, so origami never stood a chance of being ignored. Me? I was terrible at it. My fine motor skills were not exactly top-notch, so while she was crafting intricate dragons and delicate flowers, I was busy making paper planes of all sizes and launching them from my window into the backyard. Could I have imagined back then that I would one day step into the legendary Lockheed Martin factory and witness the birth of an F-16 with my own eyes? Absolutely not. Before an F-16 takes to the skies, it must undergo a series of ground tests. Every flight system, electronics, fuel supply, and hydraulics is tested on the ground first. The engine is warmed up to operational temperature, and the exhaust system and airflow temperature in the ducts are inspected. Special attention is given to the ACES-2 ejection seat and emergency systems that might be needed in a crisis. Once all ground systems pass, the pilot receives clearance for the first flight. Communication with ground controllers and engineers is checked in real time. The jet slowly rolls toward the runway, then accelerates to around 3,000 yards per hour for an optimal takeoff. After liftoff, the landing gear retracts smoothly. Everything is functioning perfectly. At an altitude of around 3,300 yards, the pilot executes the first maneuvers, testing aerodynamics, elevator, aileron, and flap responses at different speeds. The F-16 is then pushed past Mach 1 to test the afterburner system. This phase measures aerodynamic stress, identifying any defects at high speeds. G-force tests follow, as the pilot executes precise maneuvers to ensure stability under varying attack angles and velocities. After completing initial flight tests, the pilot begins the descent. At 3,000 yards, the landing gear deploys, and the pilot prepares for touchdown. The effectiveness of brakes and the auto-stabilization system is evaluated. The moment the F-16 touches the ground, it decelerates quickly. Engineers conduct final inspections of electronics, fuel systems, and structural integrity. Data is then analyzed, and if everything checks out, the F-16 is officially cleared for duty.